I begin with the Islamic greeting. Assalamualaikum warahmatullahi wabarakatuh. May God be pleased and to all of you. Selamat pagi and good morning. Right, so I'm going to use this second edition of Heat Transfer book by Sunil and Prophet Gajar. Right, we're going to look at the examples. The first example using the one-term approximation method. One-term approximation method is a solution when we solve the Fourier bio equation with specified equations and symmetry boundary condition at the center line or center point um, of the problems, right? So if you look at the this lump system or this one approximation method for the transient conduction heat transfer system, the surface, the weighted area is exposed to the fluid temperature with a constant heat transfer coefficient and fluid temperature. So this is the criteria. So if you look at the problem, we have this type of setup, and we are looking at the case when there is a changes of temperature inside the domain. Then you can use this one-term approximation method. Right, this is a physical situation of the problem, right? So you place the egg inside a boiling waters, right? So I represent this one in three-dimensional. You can put it in a square box, you can put it whatever shape that you like, but it should be in three-dimensional. So this is the way that you're going to place your physical situation of the problem. You may have a lid of the cover of these containers. It doesn't matter, right? But as long that you show this three-dimensional, so I can accept this presentation and three-dimensional, right? So why I ask this I ask this type of problem question in the problem, because in the course there is three outcome, the ability of the student to do something, right? There is three things that the student able to do. The first is to model a real engineering problem. So this is a real engineering problem. The next step is how we model this thing. So when you answer this question properly, right, and then I consider that you are able to model the physical real world. And next is how we model the problem. So we model the problem as one-dimensional heat transfer system. So if you look at the images, when I'm saying one-dimensional, is the one referred to the black line, right? So you have a center point, r equal to 0, and the maximum radius, which is r, is r0. So this a line, just a line. And then I also put additional. This you don't have to, right? If you want to put it, you can do it. But the most important thing is to have that line to represent one-dimensional, right? This is like a pencil, right? But you make it smaller. So in three-dimensional, it's just like a wire. Okay, so at the end of this maximum radius is heat transfer coefficient H, and then away from it is the fluid temperature, and the TXT tells us that the temperature varies in sorry, I will change it again to R and T, right? And then yeah, so right now the boiling temperature is higher than the egg temperature, so I'm going to change the figures, right, make it correct. Okay, now I already changed the axis label, the vertical axis labels, and I also show you the temperature distribution in the egg, right? So at any point inside the eggs, when we model it as a sphere, and this sphere is represented by one-dimensional body, right? So the temperature at the center point will be uh, the temperature gradient. I mean, the temperature gradient at the center point will be zero. There is no heat transfer there. So because it's a thermal symmetry. But at R equal to R naught at the surface of the egg, there is a heat flux. So there we will see some temperature gradient inside the solid, right? So this is what we understood from the Fourier law of conduction, right? There should be some gradient at the R naught, and at that location, the that is will be the T surface, not a T infinity. I'm going to change it again, so it should be T surface, right? Um, and then far away from it, there will be the fluid temperature. So this is another plot, and after I made some changes there, so I also add the temperature distribution inside the fluid, right? So after we have the surface temperature, there will be some temperature profile inside the boundary layers, thermal boundary layers, and then we're going to have a uniform fluid temperature away of these temperature boundary layers. So, so here I show you both the temperature distribution inside the solid, inside the thermal boundary layer, and inside the fluid. Um, and then I also show you the one-dimensional model of the egg, of the sphere that we use to model the egg. So we have an assumption here. When we model it as one-dimensional, it means that there is no temperature distribution in any angular direction, right? And then heat transfer coefficient will be a constant throughout the time. Also, the fluid temperature does not change with time. And we also mentioned that when we have something colder, we place in a hot environment, the system will be expanding. There will be a boundary work on the system, but we don't consider that. We assume that the dimension is constant in during the heating process. Right. So let us read the question for this problem. So this example for three boiling eggs and ordinary eggs can be approximated. So in this case, the author already model, right? The egg can be approximated as a 5 centimeter diameter sphere, and then the egg is initially at uniform temperature of 5 degrees Celsius. Most probably the egg is already in the refrigerator, right? So these are refrigeration temperatures, and immediately, right, suddenly, the egg is dropped into a boiling water and at 95 degrees Celsius. So for the author, his experience said that the temperature, the water is boiled at 95 degrees Celsius. But ideally, we said that the water boiled at 100 degrees Celsius. Nothing wrong with that, because when we are living, for example, in England, in northern hemisphere, up, right? So we can find that it will affect the boiling temperature of the water, and then because this involve this natural convection, so the heat transfer coefficient is very high, about 1,200 watt per meter square Kelvin. Then we need to determine the center temperature of the egg, how long it takes. When the center temperature, the center point of the sphere is 70 degrees Celsius. And I already put that information inside this Excel application software. So I just mentioned that physical situation is egg in water, and then in three-dimensional, and then the model is sphere, and I model is one-dimensional heat transfer system. And then you yeah, and then we say that this is a transient problem because it mentions specifically a location, right, in the question. And then we have the diameters. It's mentioned there as 0.05 meter. So 1 centimeter is equal to 1 divided by 100 meter. So some of the students have difficulty on units. So um, please, right, if you don't know the unit conversion when you have this online test, just open the Google and allow you to use Google. There is a unit conversion there, right? So you can use that information. I don't have any I don't allow you to use online uh, tools to help you, right, if you don't know. And then we have initial temperature, and then the fluid temperature far away from the egg, right? It can be the initial fluid temperature, it can be final fluid temperatures, doesn't matter. We assume that the water is a high temperature reservoir, and then the heat transfer coefficient is already given. So from this situation, we understand with the criteria that the temperature varies inside the domain, and the temperature varies in X. So this problem is transient problem, and because egg is a solid, even though we know that inside the egg is not a solid, but it's a liquid, form, right? So we still can consider it as a solid because there is no motion inside the egg, right? So air also can be considered as a solid in terms of in perspective of heat transfer when there is no motion, right? So we model the egg as a solid. We can model air as a solid when there is no motion of molecule inside and no motion of the body inside the heat transfer system.